Hi, my name is Jim Freericks. I'm from Georgetown University. Welcome to my presentation, which is entitled Bringing the Physics Back into the Junior-Senior Quantum Mechanics course. I do apologize that I'm unable to give this talk live and in person. We are physicists. We are not mathematicians. So let's teach the physics in our quantum mechanics classes rather than just teaching them math. The problem arises from the fact that most courses and textbooks use the coordinate representation for wave functions and the differential equation form of the Schrödinger equation. The question is this needed? And you might be surprised to learn that the answer is no. In this talk, I'm going to show you how. What we're going to do is we're going to use strategies that are derived from physics education research. We all know that quantum mechanics is non-intuitive and it's subject to common misconceptions. We also know that students really struggle with understanding the underlying meaning of quantum mechanics. Physics education research tells us to teach these conceptual ideas first and then move into the quantitative side of things. We're also going to be integrating the theoretical ideas with the experimental ideas. And in that way, we're going to be bringing the physics back into the quantum mechanics classroom. We also want to relate the theory in the class to real-world experiences in quantum mechanics. Everyone has experiences with quantum mechanical things from probably preschool, the first time when you started playing with magnets. The way that the course is structured is in 4 pieces. And in the first quarter of the course, what we do is we focus on superposition and entanglement. These are the conceptual ideas that we're trying to get across to the student, but we also develop some formalism, including Dirac notation, and we also introduce the Pauli spin matrices. What is the basis for what we're doing? We follow the ideas of Feynman, of Styer, and of Ed Taylor. These 3 people described ways in which you can teach quantum mechanics using very little math that is at the level of a high school student. In QED, the focus is on light and photons. In Styer's book, the focus is on the Stern-Gerlach experiment. And Ed Taylor showed us that by animating the different ideas that were presented, in his case primarily from the QED book, we can really get the students to learn the material well. So what we do is we actually have a set of about 50 JavaScript-based animations that we use to help teach the ideas of quantum mechanics from a conceptual side. And we start from the Stern-Gerlach experiment, and we look at the behavior of magnetic needles and current loops. But rather than introducing this in a day, we carefully go through and explain how a classical experiment would be described. And then once we have the Stern-Gerlach experiment, we can actually go into much more complicated experiments like Wheeler's delayed choice experiment. We can discuss the EPR experiments. We can show how the Bell experiments work. And we can even describe how nuclear magnetic resonance and magnetic resonance imaging works. We then introduce light. And there we start with partial reflections, moving on to single slit diffraction, 2-slit diffraction. We discuss mirrors and lenses, a phenomenon called quantum seeing in the dark, which is an interaction-free measurement. We also can talk about Hanbury, Brown, and twists, and we can bring in multiparticle physics and entanglement by talking about the Hong-U-Mandel experiment. In addition, we introduce formalism with Dirac notation, spin operators, and Pauli matrices, and from this we also can make contact with some different experiments like quantum key distribution and the phenomenon of Rabi oscillations. In the second quarter of the course, we move on to a development of the way in which we focus the teaching of the class, which is based on a representation-independent method using an emphasis on operators. And in order to do any calculation with operators, you need to work with some operator identities. This includes the Leibniz rule for the commutator of the product of operators, the Hadamard lemma, which is one of the lemmas used in proving the Baker-Campbell-Hausdorff theorem. It's the similarity transformation of an operator with respect to an exponential of another operator. We look at exponential disentangling. This is an identity that most people don't know about, but it's a property of SU2 Lie algebras, and it allows us to rewrite exponentials of Lx, Ly, or Lz in terms of exponentials of L plus, Lz, and L minus. And then we also cover the Baker-Campbell-Hausdorff theorem primarily in the Weil form, which is the simplification when the commutator of the two operators commutes with everything else. In this case, the topics and experiments that we cover in this quarter include that we develop the identities, we solve for the position and momentum eigenstates simply using these identities, and then we give a more formal description of the Stern-Gerlach and the two-slit experiments, including the delayed choice experiment that we were covering using the conceptual ideas in the first quarter of the class. Unfortunately, in this section, we really don't have any experiments to cover because this is where we're doing most of the formalism development. But even though operators are a bit unfamiliar with the students, once they get the hang of the idea that they're not commuting, working out all of these different identities and working with the identities actually comes fairly naturally to the students, and you can cover this material fairly quickly. In the third quarter of the course, this is where we really get into solving lots of problems. We develop Schrodinger's factorization method, and we show how to solve a number of different example problems using this technique. Many of you might not know about the Schrodinger factorization method. This is a technique that was developed in 1940 by Schrodinger, 15 years after he developed the original Schrodinger equation. And within this method, what you do is you factorize the Hamiltonian so that it takes the form of an A dagger A plus a constant, an energy, and then from that you can form a factorization chain, which then yields all of the higher energy excitations and all the higher energy eigenvalues and eigenfunctions. And surprisingly, every problem that you can solve analytically in a quantum mechanics course can also be solved with this factorization method. It's an easier way to get the eigenvalues because you can get the eigenvalues without getting the eigenfunctions. And it does take a little bit of getting used to, but it really is the backbone of a way in which you can develop quantum mechanics and focus more on the physics. So what do we cover in this part? We cover the simple harmonic oscillator. We look at both coherent states and squeeze states because we work with disentangling. These are actually natural and easy to cover. And the experiments that we talk about in this unit are EPR and the time of flight. We then talk about angular momentum. You can actually develop spherical harmonics without any differential equations using just operators. And the physics experiments we cover are molecular rotational spectra as described by the Morse potential. We then move into hydrogen, and here we really focus on a lot of experiments. We of course look at the hydrogen spectra, but we discuss the interesting debate about the Pickering-Fowler lines and this discovery by Bohr that it's actually ionized helium. We discuss the discovery of the deuteron and how you can find the deuteron simply by measuring light. You're actually weighing an isotope by measuring light. We talk about the charge radius of the proton, which is actually measuring the size of the proton by measuring the spectra of hydrogen. And we look at the way that you can actually picture a hydrogen atom using E2E spectroscopy, which gives an image of the hydrogen atom in momentum space. Unlike what we often say to students, which is that the position distribution in real space is what you get when you measure the electron between some position r and dr. That experiment is never done. No one knows how to do that experiment. But actually in momentum space, you can do the experiment and you do actually get an image of the hydrogen atom. So it's really nice to show the students how that works. We also go into perturbation theory, and with perturbation theory, we can then talk about hyperfine transitions, which leads us into the application of radio astronomy and precision measurements and atomic clocks. Then in the final quarter of the course, we talk about time evolution and second quantization. So the topics we cover here is the time evolution of time-independent systems. This allows us to discuss NMR spectroscopy and magnetic resonance imaging. We introduce the time evolution via Trotter product formula, which is actually a much more natural way of introducing the time-ordered product. We then talk about quantization of light. And with that, we look at how you measure a photon. We look at heterodyne and homodyne detection. We also talk about what a single photon source is and how you detect single photons. And with that and the fact that we've already covered squeezing, we can then discuss how LIGO works. So within this class, I do not teach the Frobenius method. I do not teach delta functions. I do not work with second-order differential equations and wave functions. Yet I cover all of the standard material, and the students can calculate all of the standard things that most students can calculate who have finished a quantum mechanics course. I would actually argue that in many cases, working with operators prepares you and the students for working in more advanced topics like field theory much more earlier because they're used to working with operators. So I want to encourage you to bring the physics back into the quantum mechanics classroom. I've created a word cloud here that is showing the different experiments that I'm able to cover in this one semester class. This is not a 2-semester class, 1 semester class. And then I just want to remind you that this course is actually a fully online course courtesy of the pandemic. I developed this last fall, and it's going to actually be launched on edX in the fall of 2021. So if you want to take a look at it, you can take a look at it then. And I want to thank the people who helped me develop this course. Dylan Cutler here and Lucas Vieira Barbosa were 2 undergraduate students who helped develop the JavaScript animation simulations and demonstrations that we use during the conceptual part of the course. Pia Batia and Daphne Maniatis are 2 undergraduates who helped with the developing and the coding of the course and putting it onto the edX platform. And Anna Cruz is a representative from our Center for New Designs in Learning and Scholarship at Georgetown University, who also aided us in working on the edX platform. The course is on the edX platform, and of course we were funded by the NSF in order to bring this material to you. I do apologize again because I'm not here, and I just want to encourage you that if you do have any questions, if there's anything more you would like to learn about, you can send me an email, and this is my email address, james.freericks@georgetown.edu, and I'd be happy to talk with you about any further questions that you might have on the material. And with that, I'm going to end the talk, and I hope that you enjoyed learning about how we can bring the physics back into the quantum mechanics classroom.